All right, so what we're going to look at today is indefinite integrals. Before we were looking at definite integrals where we had a range to plug them in on. You know, we went from A to B, so like from -5 to +7 or something like that. And those were definite integrals. We ultimately just ended up with a single answer. What we're going to do is indefinite integrals here, where we're not going to have limits of integration. And so what we're essentially going to get is a family of solutions. We're going to have like an infinite number of solutions that we can have here. So if you remember, our indefinite integral of a function f with respect is the set of all antiderivatives of f. So it's a set of solutions, a family of solutions, not just one of them. And it has that symbol there. And the idea here is when you take the derivative, all the constants would go to 0. So if we have an indefinite integral, then we could have essentially any constant in there that would give us the same thing, which means we can essentially just shift the graph all around and the area is going to stay the same. So it's that kind of a family of solutions. So what we end up with is we'll have an integral of f of x dx, and what we'll get is the antiderivative here plus a constant. That plus a c at the end, plus some constant, is a big sticking point where a lot of people make that mistake and end up forgetting it and messing it up. I myself included. So like I was saying, I am someone who quite often will forget to do that. You get kind of lazy and you forget to do it, but be very careful on testing stuff that you're always doing that kind of a thing. So a definite integral. So like that integral there, f of x dx from a to b is going to give you some sort of a number typically, or at least here in this class. And an indefinite integral is going to give you a function plus an arbitrary constant. Okay? So you're basically going to do the exact same thing as before, except you're going to put plus c, and then you're not going to actually plug anything into the x values. You're not going to do like the function of b minus the function of a. You're just going to leave the function and put plus c. All right, like a generalized solution here. And now we're going to look at the substitution rule here. This is how a way we can go through and do this. So if u equals g of x, so u is ultimately a function of x, is a differentiable function whose range is in the interval I, and f is continuous on I, then if we have a function f of g of x times g prime of x dx, then we can actually get this as the integral as a function of u du. All right, and this will make hopefully a lot more sense to you once we start doing it. Okay, so essentially you're going to have a function such that when you take a derivative of it, it shows up kind of elsewhere is what you're going to really look for. Okay, so we can make some things cancel out. So the primary challenge here is deciding which expression u or what expression u involving the independent variable to substitute for the integral. So you have to kind of just get good at it and get practice at it. And sometimes you don't even notice that you can do it and stuff like that. So just kind of keep your eye out on it. So let's do some examples. Okay, so if we look here, all right, we can see that if you look at it, we have two different functions in there. But notice when you look at the very first function, x cubed plus x, it has that to the 5th power, but the x cubed plus x part, if we were to take the derivative of that, we'd get 3x squared plus 1, right? And so you see that 3x squared plus 1 right there. So that's what I want to make equal to u. I'm going to say u equals 3x squared plus 1. And then I'm going to take the derivative of it, and I'm going to get du equals Oh, wait, I'm sorry. I wrote 3x squared plus 1. I meant x cubed plus x. I got ahead of myself. X cubed plus x. All right, that's the one I want. My apologies. Okay, x cubed plus x. And now I'm going to take the derivative and get du equals 3x squared plus 1, and then chain rule times dx, like that. Probably back in calculus 1, you would have just written it as du dx equals 3x squared plus 1, right? But no, we're not going to write it that way here. This notation is better because the first derivative, du dx, is algebraic. Second derivative's not algebraic. You can't algebraically manipulate it around, but this is. So we can like treat the du and dx as things, and we can multiply both sides by dx or divide by du and things like that. It is an algebraic structure. At least it acts that way. Kind of nice for us. But second derivatives, third derivatives, they are not algebraic. You can't just multiply like if that was d squared u over dx squared, you can't just multiply the dx squared to the other side, which what we can here with that. First derivatives like that are algebraic. All right. So when I do this, this is what's going to happen now. I'm going to do integral, and I'm going to substitute x cubed plus x. I'm going to put u in there. All right. So that's my first substitution. And then I've got 3x squared plus 1. And then I have dx. But dx, I use it right here, is actually equal to du divided by 3x squared plus 1. I just divided both sides by 3x squared plus 1, right? And so I can substitute that in for dx, and I get du over 3x squared plus 1, like that. And so now what happens to the 3x squared plus 1? This is where this gets to be like the payoff here. Cancels out, right? This cancels with that, and I'm left with purely the integral of u to the 5th du. And that's an integral we should be able to handle, right? What's the antiderivative of u to the 5th? There you go. So this is u to the 6th over 6th, and then what? Plus c. Plus c, right? We don't want to forget that. And now I can go back and I say, hey, u is x cubed plus x. So I just substitute that back in. X cubed plus x over 6 plus c. And there you go. Yes. Oh yeah, to the 6th power. I forgot to put the 6. Sorry. Thank you. And there you go. All right. And if you were to try to do that derivative, you would do chain rule on it. So it would become, right, if we want to check. So we'll do d dx of x to the 3rd plus x to the 6th over 6. And then that's going to be chain rule. So we got to do derivative of outer, 6 times x cubed plus x to the 5th over 6. And then times the derivative of the inner, 3x squared plus 1. The 6's cancel, and we're left with what we just took the integral of. See? So it gave us a nice answer, didn't it? And then, of course, sorry, we had the plus c, but that becomes 0 when we take the derivative, right? So no matter what constant would have been there, it would have turned out just to go to 0 as soon as we took the derivative. Okay? Constants don't change the slopes. All right. Now let's try this next one together. Sorry, anybody still writing? So let's look at this next one. Square root of 2x plus 1 dx. What do you think I should do for my substitution here? What's that? Yeah. So let's try that. Let's do u equals 2x plus 1. And then then we take the derivative, right? So this is du equals 2 dx, right? And then that tells us then that dx equals du over 2. And now, move it down a little bit here. We go and do our substitution. So our integral becomes the square root of u, and then dx becomes du over 2.
You can put a 2 in front of the square root,
oh,
and then 1/2 outside the interval.
What's that? Or you're just telling me to bring the 1/2 out front? Oh, okay. Yeah. All right. 1/2 integral u to the 1/2 du. Sorry, I thought you were telling me I missed something. And the integral of u to the 1/2 becomes
1 over 2 square root of u. So that's.
Yep. So we add 1. So u to the 1/2. 1/2 plus 1 is 3/2, right? So this is u to the 3/2 divided by 3/2, which is times 2/3. Right? Do you want me to actually write that? Sorry. This is u divided by 3/2 and then plus a c, right? And so then this becomes 1/2 times 2u to the 3/2 over 3. And then those 1s will cancel, or those 2s will cancel, right? And u to the 3/2 over 3 plus c, and then we can substitute back in, right? 2x plus 1 to the 3/2 over 3 plus some constant. And that constant could be 0, it could be a billion, any constant. Think of a constant, could be that one. Okay. All right, still writing? Okay, let's take a look here at this next one. Try this one. Try and come up with what you think the substitution should be, and then try and do it. I'm going to pause this while it all works. All right, so for this one, we're going to use u equals 5x plus 1. That then gives us that du is 5 dx, which then gives us that dx equals du over 5. So this becomes integral, not a good integral, integral secant squared of u times 5 times du over 5. So our 5s will cancel just like that. And so we just have secant squared of u. And the derivative of what is secant squared? Tangent, yep. So this gives us then tangent of u plus c, and then we can substitute back tan of 5x plus 1 plus c. There you go. Okay. What about this next one? How are we doing on that one? Good on it? Good on it? Anybody? You want me to start it or do you want another couple minutes? We have a few more to do on these other pages, so and we've got about 20 minutes left. So I think maybe I'll go ahead and get started on it. You ready? What substitution do we do? Good. 7 theta plus 3. U equals 7 theta plus 3. Therefore, du equals 7 d theta. And d theta is du over 7. So this gives us integral cosine of u du over 7. And so the derivative of what is cosine? Sine. So this is sine u over 7 plus c, which is sine of 7 theta plus 3 over 7 plus some constant. Clever little trick, isn't it? The one I posted? I can't remember when I let that get used on a test. I'll have to look. I know I remember I got that put together for one of the tests. I can't remember if I let them use it on all the tests or that one. So let me look. Ask me again sometime. All right, let's take a look at this one. Here we've got integral x squared times e to the x cubed dx. So what do you think I should do as my substitution? Yeah, derivative of x cubed gives us an x squared, and we have an x squared there, right? So let's try that. Let's do u equals x cubed, then du equals 3x squared dx, and then dx is going to equal du over 3x squared. That makes our integral x squared e to the u, and then du over 3x squared. And our x squareds will cancel, right? Cancels, cancels. That gives us then integral 1/3 of the integral of e to the u du. And easiest integral ever, what's the answer? E to the u, and then we have our 1/3 plus a c, right? And so then we keep going down here and we substitute back. This is e to the x cubed over 3 plus c. Okay? Starting to see it a little better now? Good. Try 6. If any of you can get 6, I will be impressed. Because it takes another trick added on to it. Because you should be seeing that it's not working, right? Not quite. The x's not quite canceling out for you? What substitution are y'all trying? Under the square root? So you're doing u equals 2x plus 1. Everybody? Good, that's the one I would do too. And then you get what? You get du equals 2 dx, right? And so then we get that dx equals du over 2. And so we come back down here and we have x times the square root of u, right? Times du over 2. And then we say, uh-oh, right? The x's don't cancel. So here's the other little thing. Take a look at this. I'm going to grab this part right here. I'm going to bring it over here, and I'm going to say x equals u minus 1 over 2. A little bit of algebra, right? Subtract 1 from both sides, divide both sides by 2. And I'll get integral, bring my 1/2 out front, and I'll have u minus 1 over 2 times the square root of u, du. And so then I get 1/4 integral, and now I have square root of u is just u to the 1/2, right? So this becomes u to the 3/2 minus u to the 1/2 du. And that you should be able to integrate. So take a minute and finish that integral. Again. And for anybody watching at home, there's the solution. All right, let's take a look at the next one. Sine squared of x. This one's a bit tricky too, requiring some trig identities. Or if it's already in the integral table, I don't remember if it's in that integral table. I wouldn't want you using the integral table for this one. You got to show you know how to do it. So probably not the integral table on this first test. Oh, okay. You ready? All right, so for this one, I'm going to do u equals sine squared x. And then I'm going to get du equals 2 sine x cosine x dx. Right? Okay with that? And so I have that as my option, and is that going to work for me? Okay, what if I did u equals sine x, and then that gives me du equals cosine x dx. Is that going to work for me? what if I did this? What if I said sine squared x equals 1 minus cosine of 2x over 2? And then my integral becomes 1 minus cosine 2x over 2 dx. And then that becomes, I just say here, I go u equals 2x, and then du equals 2 dx, right? And then this becomes integral 1 minus cosine of u. And then I've got a 2 here, and then this is du over 2. So sometimes you just gotta, you gotta change it, right? So for this one, that's the way you need to go through and do it, okay? I am going to maybe write one more step here. This is 1/4 integral 1 minus cosine of u du, all right? You should be able to do that integral and then substitute back, okay? All right, so you do that part, dot, 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 and you should get x over 2 minus sine of 2x over 4 plus c, assuming I didn't mess anything up. Okay? So don't forget your trig identities. Just as a quick little... All right, take a look at this one. What do we think we want to do here? Substituting in u equals e to the x, not going to work for us. Substituting in u equals x, or at least not going to work on for us very well in that one. But what if we did this? Do this. Integral, and what I'm going to do is factor out e to the negative x. And then this becomes e to the 2x plus 1 and dx. Write that up there. Y'all see how I did that? Factored out that e to the negative x. And then this equals integral e to the x over e to the 2x plus 1 dx. And then this equals integral e to the x over e to the x squared plus 1 dx. See that? And so we can do u equals e to the x, which gives us du equals e to the x dx, right? Which means dx equals du over e to the x. And if we come down here, integral e to the x, I'm going to actually leave there. And I'm going to make this e to the x over u squared plus 1. And then dx becomes du over e to the x, like that. And what happens to my e to the x's? They cancel. And so I'm just taking the integral of du over u squared plus 1. Anybody remember a derivative that turned out that way? No? Arctangent of u plus c. Arctan of e to the x plus c. I think in YOY, didn't I remember those better? Yeah, me too. You don't use them for a while, you forget them. But okay? Get that one? Okay. 9 and 10 are left. We're down to our last minute here. So I'm going to tell you to try these on your own. I'm going to give you a little hint up here. So d dx of tan x is secant squared x, and d dx of secant x is secant x tan x. So think about that when you try number 9. Okay, and then try that one, and then try 10. And we'll try and do them at the beginning of next class, okay? I'll write them out. If not, then I'll write them out for y'all to look in the notes, okay? All right, that's it.